Okay, in this video, I'm going to talk about ordinary versus singular points. And the reason this matters is we're going to have two different methods for solving a differential equation using a power series centered at an ordinary point versus a power series centered at a singular point. So we're going to have two different methods, more on that later. For now, we want to talk about how do we know which method ahead of time, what's the difference between ordinary and singular. So let's start with a homogeneous linear second order differential equation, which would look like this top line, or if you divide by the lead coefficient, you'd have something that looks like this second line. Okay, so a value of x is an ordinary point if p and q are both analytic at that point. So a point, when I say point, I mean a value of x. And I need to describe to you what exactly do I mean by the word analytic. Analytic, we mean it has a power series centered at that particular place. If our original functions a0, a1, and a2 are polynomials, then that means p and q are rational functions, and it turns out a rational function or a polynomial is going to have a power series everywhere in its domain. And so the only thing you're worried about is the denominator ever zero. So as our first example, if we have 1 over x as one of these functions, a p or a q, that's not analytic at 0 because it's not continuous, it's not defined, it doesn't have a power series. You couldn't do a Taylor series expansion centered at 0 because you couldn't take a bunch of derivatives and plug in 0. As an example, that's not a rational function, natural log x, also undefined at 0, also weird things are going to happen at 0. Okay, so that's what it means to be an ordinary point. P and q both have a power series, meaning for our purposes, if we're talking about rational functions, they have, there's no vertical asymptotes there, they're defined there, they're continuous and differentiable. So you can think about analytic as meaning continuous and differentiable. Okay, so a singular point is just a value of x that is not ordinary. So it's either going to be ordinary or singular, one or the other. Okay, so as an example, again, I'm going to stick with just polynomials as each of my a1, a0, and a2. I've already factored this to make it a little bit easier, and so if I wanted to put this in standard form, I would just divide everything by x plus 3 and divide everything by x minus 2. And so that would give us a differential equation that looks like this. And so this is my p, and this is my q. And so in order to be an ordinary point, both of these have to be analytic, and notice both of them are going to fail to be analytic at 2. When you plug in x equals 2, you have a 0 in the denominator, which means it's not continuous, it is not differentiable, weird things are going to happen. Also at negative 3, both of these are going to have weird things happen. So x equals 2 and x equals negative 3 are both singular points. I should also point out, in this example, we have the same denominators in both. If for some reason we only had like a single power of x plus 3 and 1, that still would mean that negative 3 is a singular point, and because we have at least one of the functions, p or q, is not analytic at 2, 2 would still be a singular point. Okay, so we don't need to have both of them be not analytic. If either one or both is not analytic, then we would say that's a singular point.